Hello, everyone. Welcome back. So today I'm going to be talking about higher order derivatives. So this is the first lesson in Unit 3, which is the unit about the applications of derivatives. So why do we actually care about derivatives, and what else can derivatives represent? So we're going to talk about how derivatives can help us to find the velocity and the acceleration when we have the distance function. So in this example, it says, let S of t represent any distance function where t represents the time. That means that the first derivative, this one right here, is the velocity function. We can find the first derivative to get the velocity. Then, to find the acceleration, we can take the second derivative, or in other words, the derivative of the velocity, right? Which velocity was the first derivative. Or to find jerk, we can take the third derivative. It represents the jerk function, which represents a sudden jerk or sudden change in acceleration with respect to the time, and it's labeled j of t for jerk. So basically, we can figure out the velocity, acceleration, and jerk using what we have here. Let's go through an example. Example 1 says, a drag race car's position from the starting line is given by this equation. Find the velocity and acceleration as functions of t. So to find the velocity, we know that the velocity is the same as the derivative of the original function. And we can very simply find that just by using the power rule, nothing too fancy here, and say that it's going to be 6t squared plus 36. And there we have it. Now to find the acceleration, that's equal to the second derivative, right, which is the derivative of the velocity function, and that's going to be 12t. And then the 36 just disappears because the derivative of a constant is just 0, right? And so that's the answer there. And they didn't ask about the jerk, but if we were to find the jerk would just be 12. Good. All right, let's move on. This one says a water rocket is shot upward at an angle. The height function s of t in meters of the rocket above the ground is represented by this function where t is the number of seconds. Determine the maximum height reached by the rocket. Okay, so remember, to find an optimal value or the maximum or minimum, what do we have to do? We must set the derivative to equal to 0 in order to find the maximum or minimum. We could also actually find that by completing the square. However, that's not what our lesson is about today. Our lesson is about using the derivatives to find the minimum or maximum. In this case, it'll be a maximum. Okay, so basically, we're going to set s prime of t equals to 0, because when the slope of the tangent is 0, that means we have a turning point. We're at a minimum or a maximum in those situations. In this case, it'll be a maximum. So let's do that. S prime of t is equal to negative 10t plus 30. So if 0 is equal to negative 10t plus 30, that means 10t is equal to 30, and that means t is equal to 3. So t represents the time that the maximum height will be reached at. And they didn't ask what time will the maximum height be reached. They asked what is the maximum height. So we need to actually plug this into our original equation to find out what is the height at 3, right? At 3 seconds, we know that's the time that will give us the max height. So s of 3 is negative 5 times 3 squared plus 30 times 3 plus 1, which is going to be negative 5 times 9 plus 90 plus 1, which is going to be negative 45 plus 90 plus 1, which will be 46. So therefore, the height, or I should say the maximum height, is 46 meters. And sometimes you might be asked just, what's the t value? What time will it be when the rocket reaches its maximum height? In which case we could stop here and just say this is our answer. In some cases they might ask for both, and in some cases they might just ask for the height. But in order to find out what the height is, we first have to figure out, well, what is the time that that height will occur so that we can figure out what that height is. Okay. B says determine the velocity of the rocket when it is 1 meter above the ground. Okay, so when the height is 1 meter above the ground, what is the velocity? Is basically what they're asking here, right? So remembering that the velocity is when we take the first derivative of the function, and they'd like to know when the velocity of the rocket, what is the velocity? When our height is 1 meter above the ground. So in order to do that, we have to figure out, okay, well, what time will that occur, right? What time is that going to occur when the rocket is 1 meter above the ground? So when the rocket is 1 meter, so s of t would be equal to 1. That means 1 is equal to negative 5t squared plus 30 plus 1. So the 1's cancel. We're just going to get 0 equals negative 5t squared plus 30t. Ooh, I forgot the t there, but I meant to write it. So that means that we're going to have negative 5t times t minus 6, like that. And that means t equals 0 or t equals 6. Those are the two times when when the rocket will be 1 meter above the ground. Those are the two times where that occurs. Now we want to know what is the velocity during those two times when we're 1 meter above the ground. So again, velocity is equal to s prime of t, which is negative 10t plus 30, as we established before. So now what I'm going to do is I'm going to plug in these two values. So let's see, s prime of 0, which is same as velocity of 0, is going to give us 30. S prime of 6 will give us, let's see, negative 10 times 6 plus 30, which will give us negative 30, right? So 30 backwards, in other words. However, that's not really going to work for us. We just need to say that the answer is 30, right? We just need the positive 30. We don't actually need to go in with the negative 30 at all. So therefore, the velocity at 1 meter is 30 meters per second. All right, well, there we go. All right, let's move on to another example. This one has a bunch of different parts to it, and let's see if we can do it. It says the position of an object moving on a straight line, where s is meters and t is seconds. Assume a positive direction is moving right and the negative direction is left. So what they mean by that is that if we get a positive value, then that denotes, so to speak, moving right. And if we get a negative value, so going backwards, that is moving left, right? And it's important to define those things because generally positive means up and negative means down or backwards. So it's important to say, okay, which way, when we're talking about left or right, which way is forwards? Which way are we considering to be forwards in the situation? And which way are we considering to be, oh, that's backwards? We're going backwards in that case. Very good. Okay, so let's answer the first part of this question, which says determine the velocity and acceleration at t equals 2 seconds. Well, first we got to find the general velocity and the general acceleration if we are to find them at 2 seconds. So let's do that. So the general velocity is equal to the first derivative, and the general acceleration is equal to the second derivative. So what's the first derivative? Well, according to the power rule, it's going to be 12t minus 3t squared. And the second derivative, according to the power rule again, would be 12 minus 6 t. Now we need to plug in t equals to 2. Okay, so v of 2 is equal to 12 times 2 minus 3 2 squared, which is 24 minus 12, which is 12. Velocity, or sorry, not velocity, acceleration 2 is equal to 12 minus 6 times 2, which is equal to 12 minus 12, which is 0. So therefore, there was no acceleration at t equals 2. It was going at a constant rate. And the velocity at t equals 2 would be 12 meters per second. All right, and actually, let's add units here. So we're going to do meters per second here, and this would be meters per second squared, or meters per second, because it's referring to acceleration. So therefore, it's 12 meters per second, which we're saying that means we're going right, based on what we were told earlier. All right, now it says, what direction is the object moving at t equals to 5 seconds. So first, to do this, we're going to need to find the velocity v of 5. And if it's positive, then that means it's moving right. And if it's negative, that means it's moving left. So let's see what we get. So v of 5, let's see, 12 times 5 minus 3 times 5 squared is equal to 60 minus 75, which is negative 15 meters per second. So that means the object is moving left in this case, because back in the question they told us assume a positive direction is moving right and a negative direction is moving left, and we ended up with a negative direction, right? We ended up with a negative velocity when we figured it out. Determine at what time the object is at rest. Okay, so the object is at rest when the velocity is 0. So we need to set v of t, the velocity, or the rate we're going at 0, right? We want to be going 0 meters a second, because when we're going 0 meters a second, that means that we are at rest, right? Okay, so let's do that. That is going to be 0 is equal to 12t minus 3t squared, which means that, let's see, we can factor out a negative 3t, and over here get negative 4, and then here get plus t. So that means that t equals 0 and t equals 4. So the object is at rest at 0 seconds and at 4 seconds. So those are the two times the object would be at rest. All right, there we go. So therefore, the object is at rest when t equals 0 and t equals 4. The next question asks, when is the object moving right? So we know that the turning points, or the points where the object is at rest, are 0 and 4. So that means that between those points and after and before those points, we need to figure out if it's going to be going right or going left in those cases, okay? Now, in this case, we actually don't have to do before 0 seconds, because that wouldn't make any sense. At 0 seconds is at rest, so there's two intervals I'm interested in. I'm interested in the time that we're between 0 and 4, and then I'm also interested in the time where t is greater than 4, okay? Because we know that it's at rest at 4 and at 0, but we don't know what's happening in between. So what I'm going to do for these intervals is I'm going to plug in any value within the interval, right? Because in order for the object to switch directions, it first has to be at rest for a moment before it can actually switch directions. It won't instantly switch, or it won't instantaneously switch. It'll stop and it'll go backwards. It'll go the other way. So therefore, for this one, I'm going to just use t equals 1. And here I'm just going to use t equals 5. But I want to be clear, you can use anything on this interval, and it will speak for the whole interval. The important part to make sure of, though, is that you're accounting for all intervals that are possible, considering when the object is at rest. So let's say the object was at rest a third time, we would have to we'd have a third interval here. So it depends how many times the object is at rest, and if we could go before 0 seconds, if that was something that made sense, we would have to do that as well. The reason we're not doing that is because that doesn't make sense for the situation. So let's try it. What's v of 1 and what's v of 5? Okay, so v of 1, let's go back to what's velocity. It is 12 times 1 minus 3, 1 squared, which is 12 minus 3, which is 9. So that's a positive number. The other thing I was noticing there just now as well is we already actually calculated v of 2, and v of 2 is also in the interval from 0 to 4. So we could even just say, oh, based on our previous work, we got a positive answer there as well. And so therefore, it would be moving right in that part of our question. Okay, now let's see. Do we have a v of 5? Actually, we already have v of 5. We already calculated v of 5. That was negative 15 earlier. So actually, both of them, we could have just looked at previous work we'd done and figured it out, but that's okay. We also don't have to. And we get that it is negative 15, so it's negative. So therefore, the object is moving right from 0 to 4, right? But it's moving left from 4 and beyond, right? From anything beyond 4, so we don't include that interval. So this is the interval we're looking for. Now, if the question asked when is the object moving left, we would give the second interval that t is greater than 4, but that's not what we were asked. We were asked when the object was moving right. So I'm going to say, in conclusion, the object is moving right on the interval, not equal, sorry, from 0 to 4, or another way we could write it, if we wanted to use a different notation, we could write like this as well. It doesn't actually matter as long as you write the correct interval. That's what matters. Okay, when does the object return to its initial position? Okay, so basically the initial position would occur when s of t is 0. So when else is s of t 0 other than at 0, right? Because obviously at 0 it's at its initial position, but when else is the question. So let's set 0 equals to s of t, which is 6t squared minus t cubed, and we're going to factor this and say 0 is equal to t squared times 6 minus t, which means that t is equal to 0, which that we knew, right? We knew that at t is 0 and the time is 0, we'll be at our initial position of 0. And also, t is equal to 6. So that's the answer, right? It didn't ask where it was because they told us in the question, right? They told us it would be at its initial position. They asked when does the object return to its initial position? And the answer is the object returns to its initial position after 6 seconds from our start time. So we'll just say after 6 seconds. Very good. All right, this last question says, draw a schematic line diagram. Show the position of the object over a 7-second period, including all extreme positions. So what happens to it first? Well, first we're at t equals 0 and our initial position. Then we are going to go from 0 to 4, right? We go right for 4 seconds here. So this is going to be t equals to 4. Then it goes back to its initial position. So first we go forwards. And then we go back to the original position at t equals 6 seconds, right? So we're going to go back, and then at t equals 6 seconds, we're back at the same original position. And then we're going to continue to go left for one more second. Well, actually, infinitely will continue that way, but they only asked for over the first 7 seconds as to what happened. Good. All right, well, there we go. That is it for today. Next time, we're going to be talking about minimums and maximums over intervals and go over some other applications as well. But that is all for today. Goodbye, everyone.